Okay, great. Thank you. So I think now we move to the last talk for today, which will be given by Professor Steve Kivelson from Stanford University. Professor Kivelson, could you please start to share your screen?
There we go.
Okay, so
good.
His talk
can you hear
is
me?
about, yeah. Yes, we can hear you. Yeah. Professor Kivelson will give the talk on some theoretical considerations concerning Wigner crystals. Please go ahead,
Yeah.
Professor.
So first place, I'd like to apologize. I'm not going to have the beautiful slides as everybody else did, but I've honestly been having a hard time concentrating given the situation in the world around us. It's common in giving these talks to have pictures of Einstein, or in this case, maybe Wigner, to presumably convince the audience that the talk is profound on that level. I've instead given you a picture from a Syracusean coin of the nymph Arethusa to hopefully convince you that what I'm going to tell you is classic, and also to remind myself that elections are not quantum systems, and checking the latest poll numbers doesn't affect the outcome of the election. So what I'm going to talk about is largely old results. Hopefully, well, first place, I'm getting old, that's the bad part. But many of these may be old enough that not everybody here knows about them. This is work in collaboration with Boris Spivak, and even older work in collaboration with Shadip Chakravarty and some other people. And I'll give references both to this and to some other work at the end of the talk. So as we've heard, there's an important dimensionless control parameter that governs the phases of a two-dimensional electron gas at zero temperature. It's the ratio of the typical potential energy of interaction to the kinetic energy of the electrons. And for Coulomb interactions, that goes like the density to the -1 over the dimension power, which means in 2 dimensions, it goes like the density to the -1/2 power. It also goes like h bar to the -2 power. So large RS is both more classical and more potential energy dominated. I just want to remind people, however, that this is a feature of Coulomb interactions. If we had short range interactions, for instance, in 3 dimensions, then the classical physics, the crystal physics, will occur at large density, and the quantum physics will occur at low density. So at large RS, at small RS, we have familiar metal physics. There's Fermi liquids, there's whatever other physics we're familiar with. At large enough RS, we have the Wigner crystal, and there's a critical value of RS called R sub C. And above that, we have a Wigner crystal, and below that, we have other phases. And there's this classic work that's been referred to several times that was numerical studies that came out with a critical value of RC that was on the order of 40. Now, there are quantitative issues with this that actually I'll get to later in the talk. Among other things, this is a non-universal quantity. It certainly should depend on microscopic details of the system one is looking at, mass anisotropies, thickness of the two-dimensional electron gas. And there are also some theoretical uncertainties about this, but I think there's no question that this result is qualitatively correct, and it's extremely important. And it's important in the sense that it's the largeness of this critical RC that's responsible for the existence of something called highly correlated electron fluids. So the point is that there's a broad range of RS in which RS is big compared to 1, but smaller than RC. In this case, one has a fluid, and therefore one can't understand this by expanding about the large RS limit because you're starting in a wrong phase of matter. You're starting in a crystalline phase. And on the other hand, RS is quantitatively large compared to 1. So one can't imagine doing perturbation theory in the interactions. The perturbative approach or any resummed perturbative approaches like RPA or perturbative renormalization group are really without theoretical justification in this regime. This isn't unique to this quantum problem. This is really the problem of liquids, and even within this problem of the two-dimensional electron gas, a similar problem occurs if we just take classical Coulomb interacting systems. Tc is a number of order 1 times the typical interaction between electrons, but that number of order 1 was calculated even longer ago by Chakravarty and collaborators to be something like 1 over 125. And so there's a regime of highly correlated classical fluids when the temperature is small compared to V, so that the system is in no sense a gas, but still larger than gamma C, in which we have a highly correlated classical Coulomb fluid. All right, so my topic, the topic of this conference is not the fluids, but the Wigner crystal phase. So let me say a few things about the Wigner crystal phase. So the first thing is that the Wigner crystal phase is an insulator. The resistivity diverges exponentially as one tends to low temperature. The activation energy is the energy to create the lowest lying charge carrying excitation, which is probably an interstitial. It's easy to access conditions where you would see this and in which nonetheless there's no worry about Froelich sliding conductivity. So this is really the properties of an insulator. There's something that's a little bit less obvious, which is what happens to the spins. So once we've localized the electrons to form a Wigner crystal, there is still physics to do with the spins. And this is governed by some exchange interaction between the electrons, some tunneling process with amplitude K, which one could estimate using semi-classical methods to be some phonon frequency of the crystal times e to the minus the action for a tunneling path. The action will have some WKB-like expression where it's an integral over the length of the tunneling path times the square root of the mass times the height of the barrier that you're tunneling through. The distance of the tunneling path then is going to be on the order of the spacing between electrons. The height of the barrier is going to be on the order of 1 over the spacing between the electrons. So one finds that the action associated with a exchange interaction will go like some number of order 1 times the square root of RS. And hence will be exponentially small at large RS. So what do we learn from that? Well, first place, we could be in a temperature regime in which the temperature is still small compared to the melting temperature, so we still have a Wigner crystal, but large compared to the exchange energy. And in this region, the exchange interactions can be neglected. And in that case, the spins are totally disordered, which means that there is a entropy n log 2 associated with the spins in the Wigner crystal. And this is a somewhat surprising feature of a Wigner crystal. The Wigner crystal is a crystalline ordered phase, but it is also a large entropy phase. And what that means is that a Pomeranchuk effect is possible, something that I will get back to later in this talk. It also means that the system is highly polarizable. As long as B is higher than the temperature, then all of the spins will be spin polarized. And since the magnetization density will be the electron density times the Bohr magneton. So if we go down to 0 temperature or low temperature, we're going to have to take into account the exchange processes. And so, as I said, the exchange processes one can estimate by some sort of a WKB calculation. Here, K sub n is going to represent a process in which I interchange n electrons, and then our hope is to calculate these dimensionless numbers alpha n. And this is something that that I did in collaboration with Shadib Chakravarty and friends some time ago. And so let me just give you a sketch of this. Here on the left-hand side of my screen is a sketch of a Wigner crystal. And I've shown several possible exchange processes. Here in red is a 2-particle exchange in which this particle interchains with that particle, thereby generating an effective interaction between the spins on these 2 sites. Calculating these things is a little bit complicated because, as you can imagine, the exchange amplitude depends exponentially on the classical action. And so one wants to get the lowest possible classical action. And as, for instance, as these 2 particles are exchanging with each other, undoubtedly neighboring particles are going to be moving so as to get out of the way. We do our best to handle that problem. And in this way, we obtained estimates for these various coefficients alpha that come into these exchange interactions. And I've listed them here for the 2-particle exchange, the 3-particle exchange, the 4-particle exchange, 5-particle exchange not shown, and the 6-particle exchange. And there are a couple of things about these numbers that are a little bit surprising. One is they're all relatively similar to each other. This is surprising because, of course, the multi-particle exchange processes involve tunneling over longer distances. But on the other hand, these ring exchange processes tend to have lower barriers. It doesn't bring electrons close to each other, so the barrier heights are smaller, and hence many of these exchange processes are remarkably similar to each other. So that's the first thing to notice. And the second important thing to notice is that of these, the smallest alpha, that is to say, the largest exchange process in the large RS limit, is the 3-particle exchange. So what do we learn from this? Well, first place, we learn that we have a highly frustrated quantum magnetism problem. And there is a tendency, which I'm afraid we also followed, to say that if we have a frustrated problem of quantum magnetism that we can't solve, probably the solution is a quantum spin liquid. But whether or not that's true, what's certainly true is that for large RS, K3 dominates. And the interesting thing about K3 is that there is an old theorem by Thouless that if you have odd particle exchanges, that mediates ferromagnetic interactions. So what this means is that at large enough RS, where the 3-particle exchange dominates, which occurs presumably for RS bigger than some critical value RF, that the Wigner crystal should have a ferromagnetic ground state. To estimate RF, what we did was we calculated the contributions of the different up to 6 particle exchanges to the nearest neighbor S.S exchange interaction. And okay, it's some combination of contributions from 2, 4, and 3 particle exchange. And we asked at what value of RS does this change sign from being negative at large RS to being positive at smaller RS. And we got a critical value of 40. Okay, I don't ask you to believe that that's quantitatively correct, but what that means is that RF is of order RC. And what that means is that all or much of the Wigner crystal phase is going to be ferromagnetic. Okay, so let me get back to the comment that I made about calculating RC. So the calculation of RC was really a landmark achievement in condensed matter theory. So I don't want this to be taken as critical. I think that's really a major advance in the field. But there are 2 things about it. So the first is that this comes from comparing 2 energies and asking when they cross. And of course, it can't be more quantitatively correct than the energy of the worst of these states. And for instance, we don't really know what the magnetism is on either side of this phase transition. So there should be some quantitative uncertainty about these. But there's a more interesting issue, which is the next issue that I'm going to address, which is that we can prove a theorem that first order transitions are forbidden under the circumstances of being in 2 dimensions with Coulomb interactions. And therefore, there isn't actually a direct phase transition from the Wigner crystal to the liquid phase. Rather, what we show is that there must be intermediate phases between these 2 phases, likely microemulsion phases. So let me describe how this proof works. I originally had planned to actually go through the steps of the proof, but I decided I don't have time for this. But let me at least describe the logic of the proof. So the proof is a proof by contradiction. So first, assume that there is a first order phase transition between a Wigner crystal and a Fermi liquid. So here I've sketched that situation here. I've looked at the density as a function of n bar. N bar is the positive background charge. Since we have a long range interaction, which falls off more slowly than 1 over r to the d, we can't tune the density by tuning a chemical potential or something. There's a constraint of charge neutrality. And that's also responsible for the fact that even though this sketch shows a concave energy, the system is not unstable to macroscopic phase separation. The long-range Coulomb interaction makes macroscopic phase separation illegal. And so the proof goes like this. If this transition occurred, then then at this critical density, we would have a phase which could either be a Wigner crystal or a Fermi liquid, but its energy would be E0, the energy of their crossing. What we do is we construct a state with lower energy by making a alternating array. Here I've drawn it as stripes, but it doesn't matter, of region of Wigner crystal, region of Fermi liquid. I transfer electron density from the Wigner crystal phase to the Fermi liquid phase, sort of like phase separation, but now on a mesoscopic scale, and show that I can pick a length scale L large enough compared to the correlation length that these considerations apply, in which I can construct a state that has lower energy than E0. And therefore, the assumption of this crossing is internally inconsistent. There must exist intermediate phases. It, of course, suggests that the construction I use to prove that might well be the right answer, and that the right answer might be some microemulsion in which we have regions of Wigner crystal and regions of Fermi liquid. Of course, it could also be some totally different phase. So probably it means that between the Wigner crystal and the Fermi liquid, we have microemulsion phases, which for instance look like this, with regions of Fermi liquid and regions of Wigner crystal. And you can imagine all sorts of ways that something like this could give rise to an apparent metal insulator transition by percolation and so on. So let me end by talking about the Pomeranchuk effect and how this might lead to interesting behaviors. So suppose we form a microemulsion phase, and so the important characterization of that microemulsion phase is going to be the volume fraction or area fraction of the system that's a Wigner crystal. And that's going to be some function of the difference in free energy between the uniform Wigner crystal and the uniform Fermi liquid phase, which will be equal to the difference in their energies minus the difference in their entropy times their entropies. And if there's a magnetic field on, also minus B times the difference in their magnetization densities. So at least over a broad range of temperatures, the Wigner crystal has an entropy that's log 2. The Fermi liquid has an entropy that's small, it's T over EF, and therefore the entropy of the Wigner crystal is large compared to that of the Fermi liquid. Similarly, the magnetization density of the Wigner crystal in the presence of even a small magnetic field will be 1, whereas for the Fermi liquid, it will be of order B over EF. So what that means is that the fraction of the system that's going to be Wigner crystal is going to be a linearly increasing function of temperature or increasing function of applied magnetic field. So this gives rise to a very interesting possibility, a possibility of getting a thermodynamic origin of a temperature dependent of a resistivity that might look metallic in the sense of being an increasing function of temperature, even if the notion of a temperature dependent mean free path was irrelevant. So for instance, let's think about taking the derivative of the resistance with respect to temperature by a sequence of partial derivatives. I'll express that as the derivative of the resistance with respect to the volume fraction of Wigner crystal, which I think should be negative. Positive. The resistance should go up as the amount of Wigner crystal goes up. It's times the derivative of the fraction of Wigner crystal with respect to the change in the free energy, and then the derivative of the change in free energy with respect to temperature. So it gives me some things that depend on all sorts of complicated microscopic details and transport times the difference in the entropy between these two phases. And similarly, if I tried to calculate the derivative of the resistance with respect to an in-plane magnetic field, I would get the same complicated prefactors, but then multiplied by the change in the magnetization. And since both of these quantities are going to be positive, I have an explanation for a large linear magnetoresistance and a T-linear contribution to the resistivity. Okay, so that was really what I wanted to say. Here are some references. These are some of these classic references that I referred to estimating when we have a Wigner crystal at 0 temperature. These have already been referred to, I guess. Here's the Monte Carlo calculation of the freezing temperature of this Coulomb gas. Here's this really interesting Thales paper. Here's an earlier semi-classical calculation of the multi-particle exchanges in the Wigner crystal. This is the paper from which the numbers that I cited came. And here are the various papers on the non-existence of a direct transition and the existence of microemulsion phases. So let me then summarize what I would like you to take away from this. So first place, as we all know, the Wigner crystal occurs above a large critical R, and that's very interesting. But that one should also take away that at least over most of the range, the ground state of the Wigner crystal is likely to be ferromagnetic. And this could depend upon details of the microscopic physics. If RF is bigger than RC, then there is an interesting region of frustrated antiferromagnetism close to the edge of the Wigner crystal regime, and that's an interesting open question to understand exactly what's going on there. There's no direct transition between a Wigner crystal and a Fermi liquid possible. Rather, one should be looking for intermediate phases here, and in particular, in these intermediate regions of intermediate phases, the Pomeranchuk effect is likely to have a significant influence on the physics. All right, thank you.
Great. Thank you very much for your wonderful talk, Professor Kivelson. We are right on time, so we have time for a few questions. Yes, Professor Vogler, please go ahead.
Misha, you're...
Sorry, I forgot to unmute myself. Yeah, I said,
Okay.
Thank you for this talk, Steve. I wonder if you thought about the effect of additional periodic potential on this question of crystal to liquid transition, or maybe this intermediate phases.
Right. Let's see. I have thought about it. I've got a number of random thoughts on it. So first place, I've started with the assumption that the Wigner crystal to Fermi liquid transition, if it's direct, should be first order. There are a variety of arguments for that. One is if the Wigner crystal is triangular, then at mean field level, they're cubic invariant, so it must be first order. There's also the Brozovsky argument of that even if we didn't have cubic invariance, that the transition would be fluctuation driven first order. If we put the right sort of periodic potential and the right amounts of symmetry breaking, it's quite possible that one could have a continuous Wigner crystal to liquid transition. And in that case, I don't have anything to say. So that's an interesting loophole. I guess that's really the most, unless there was something else you had in mind.
No, I don't have. I just wondering if you already thought about it.
Yeah. Then the other thing is that this theorem assumes that both phases are compressible. So you could imagine transitions involving the lattice to an incompressible phase in which the Wigner crystal is commensurately locked to the underlying lattice. And again, then the considerations are quite different.
Okay. The next, are we done with this question?
Yes, thank you.
A follow-up question.
Okay. Okay, the next question will be from Professor Kim-Fa-Mak.
Hello, thank you for the very nice talk. I'm just trying to make a connection on the discussion with the magnetism for Wigner crystal with the electron crystal phase in Moiré superlattices. So in that case, can I think of it that the electron crystal phase in Moiré superlattice requires a smaller RS because of the presence of the lattice, so that once you get into a commensurate filling factor, then the system just crystallizes. Then I will get into the regime sort of easily that the RC is much smaller than the RF, right? Then right. I can get into an interesting antiferromagnet if the crystal symmetry for that electron crystal phase is, is frustrated, for instance.
Right. Yes. So, I think that, well, so first place, the presence of the periodic lattice or of the Moiré lattice will affect the semi-classical calculation. So I don't guarantee that even for large RS that ferromagnetism is the universal answer. It is, I think, unless we've made a mistake in our semi-classical calculations, it's correct for the triangular lattice in the continuum. But as you saw, the numbers, the pair exchange and the 3-particle exchange were very close to each other. So I can imagine that even at asymptotically large RS, the answer about whether you get ferromagnetism at all could be different in different circumstances. But that at any rate, I certainly agree with you that if you manage to stabilize the crystal in one way or another at smaller RS, then certainly the considerations become much more interesting and all of these frustrating interactions become very significant.
Yeah, I asked this question because basically in all this fractional filling that we have, this electron crystal states with the Moiré superlattice, they are all antiferromagnet, right? They are all antiferromagnetic from the Curie-Weiss law. Yeah.
Yeah. So you would certainly think that in general on the lattice, that the pair exchange is going to be the dominant one, and that therefore it's going to be dominantly antiferromagnetic. So this is special to the crystal. I mean, it also, I meant to look it up, but I remember there were calculations in crystalline helium-3 that show that at high pressure, it should be a ferromagnet for the same reason that 3-particle exchanges are dominant. But that has to do somehow with the behavior of the continuum and the existence of relatively low energy shear motions that allow exchange of multiple particles that are not accessible to the 2-particle exchange. Otherwise, 2-particle exchange should dominate.
Okay, thank you.
Okay, we have plenty of more questions. The next will be from Professor McDonald, please.
So Steve, I was going to ask you, so the argument about, Wigner crystal to Fermi liquid phase transition applies to any density driven first order phase transition.
Correct.
Or does it, or was there something special?
No, it's any density driven first order phase transition. And, our proof applies if you have 1 over r to the x, and actually there's versions of the proof that work for all x in the range between 2 and 3 in d equals 2. So it's for any density driven transition, and as long as there are interactions that are long range by this definition.
Right, so the conclusion is that you have to go through a state that breaks translational symmetry possibly on some long length scale.
Not necessarily. So that's so what it is that I can show it's suggestive of that, but it doesn't prove it. What it proves is that a state like that has lower energy than the state that would occur if you just said there's a first order phase transition. It could be that there's some totally different state that has still lower energy. It's really the part that's a proof is a proof by contradiction.
Yeah, but so, if you go, you go from one state to another state somehow.
Yeah, so the very likely thing is, for instance, you could go through stripe phases, and you could go from a stripe phase that was mostly Wigner crystal with little bit far separated stripes of Fermi liquid to a stripe phase that's mostly Fermi liquid with little stripes of Wigner crystal, or with, you could do that not with stripes, but with bubbles. You could get the bubbles and then the transition from the microemulsion phase to the uniform phase would be some sort of Lifshitz transition where the wavelength of the order diverges as you approach the transition.
Okay.
All right, the next question is from Professor Shayagan.
Oh, hi, Steve. I'd like to ask a little more about the role of anisotropy in that system that I was talking about this morning. It turns out the Fermi, the Fermi contour is anisotropic, this effective mass anisotropy factor of 5. How does that affect the Wigner crystal phase? Are there any quantitative, qualitative changes that you'd expect?
Right. So, so that's a really good question. I've been thinking about that. I mean, so as RS goes to infinity, and as the electrons get very far apart, it has no effect.
That's correct, right?
But as RS gets to be finite, you know, the fluctuations about the Wigner crystal site become anisotropic. That will cause the Wigner crystal itself to become anisotropic. It could cause phase transitions, say from a triangular to a square or something. I don't know. There's all sorts of interesting things that it could do. And it could also affect the balance of these different multi-particle exchanges. So, you know, I've of course been triggered to start thinking about this problem again by all these beautiful new results that you have found. I should have mentioned that although I didn't discuss any experiments here, I had certainly very much in mind your new experiments. And this is a clear issue that needs to be addressed before any direct comparison can be made.
Thank you.
The last question probably, oh, Philip. Okay, the last 2 questions. Jong-Yong, please.
Oh, yeah, I just, maybe I missed something, but in the proof, how was the exponent of the interaction matter for this between Fermi liquid and Wigner crystal?
How does the X mean the 1 over R to the X?
Yeah, I'm not.
I didn't describe it. I mean, you know, if you have another 10 minutes, I can sketch the proof. But I skipped the proof. I didn't explain to you how.
Is there a reference?
So in fact, it turns out there are 2 completely separate proofs in this region. For X less than or equal to 2, you have long-range interactions, and so macroscopic phase separation is impossible. And so the proof is that mesoscopic phase separation has lower energy than in a uniform state. For X between 3 and 2, no, I got that backwards. 3, yeah, greater than or equal to X greater than 2, we have short range interaction. So macroscopic phase separation is possible. And the proof is that mesoscopic phase separation has lower energy than macroscopic phase separation. So in fact, there are 2 totally different proofs. At the end of the day, you lose track and they actually look pretty much the same. But this is the range in which the proof applies. And okay, it's in our papers, or I can sketch it. You can contact me and I'd be happy to sketch it to you. There. Now you understand.
Okay, thank you.
Philip, the last one.
Yeah, I think it's a beautiful talk, Steve. I would just wonder that how much this picture will change under the magnetic field, especially in connections with the, say, Plato to Plato,
right, quantum
system.
So first place, this proof of microemulsions applies in the magnetic field as well. That's unimportant. The nature of the phases does matter. So certainly in a magnetic field, magnetism, the spin magnetism is going to be quenched. There's all sorts of interesting first order what should be first order phase transitions, like from a quantum Hall liquid to a Wigner crystal. The considerations here have to be slightly modified in that case because the quantum Hall state is incompressible. And so it's something that I'm working on. There's a lot of interesting, themes and variations based on this that can be worked out. Okay, that was a long-winded way of saying it's an interesting question, but I don't have a good answer to it.
Great to hear.
All right, I think the last session is concluded. And thank you again for all the wonderful talks today. Hong Kong, I'll give the control back to you.
Okay, I think that we'll move on to the informal discussion session, open discussion session run by Eugene.
So, yeah, but shall we give people like at least 10 minutes to rest? I think we're behind the schedule, but yeah, I think. Yeah, so shall we reconvene at 5:15 then?